Welcome to the next session on finite element analysis. In this session, we are going to discuss about the advantages of serendipity elements in FEA. In finite element analysis, serendipity elements refer to a specific type of finite element shape function that provides a convenient and efficient way to interpolate the field variables within the elements. The term serendipity is used because these elements offer additional interpolation points between those strictly necessary for the polynomial degree of the element. These additional points often lead to unexpected benefits or advantages during the analysis. So suppose if you are talking about an element like this, if you see here, 1, 2, 3, 4. These are the regular nodes of a rectangle. But when you provide additional nodes like 5, 6, 7, 8, this is what helps you get a better solution. Because more the number of nodes, better will be your solution. So when you have more nodes, which is beyond the polynomial degree of the element, it will help you get better results, and that is nothing but serendipity in FEA. Here are key elements and advantages of serendipity elements in FEA. Additional nodes. Serendipity elements have additional nodes compared to standard elements of the same polynomial degree. These extra nodes are strategically placed to improve the accuracy of the element's representation of the physical behavior. So as I just told you, suppose if you are talking about a three-noded triangle, then you will have 1, 2 and 3 as the three nodes. But if you add more nodes, between node 1 and 2, you will add node 4. Between node 2 and 3, you will add node 5. And between node 1, 3, you can add node 6. So here I have made a 2D 6-noded triangular element. So this will help you get better results. As this word says, nodes are strategically placed. That is what I just explained, that 4 is between 1, 2, 5 is between 2, 3, and this will continue. Now suppose if you want to add more nodes, then how will you start? Between 1, 4, you will add the next node 7. Between 4, 2, you will add 8. Then you will go between 2 and 5, node 9, and accordingly you will continue. Now this can continue till you want to stop and you want to get a result with a particular number of nodes. But you can keep on adding nodes based on your accuracy required. More the number of nodes, better will be the solution and more accurate you will get solution. Same way, here I have created a 8-noded rectangular element. 1, 2, 3, 4 are the 4 nodes of a rectangle in general, as we know. But apart from 4 nodes, you can also define this rectangle with the help of more number of nodes. So between node 1, 2, I have given node 5. Between 2, 3, I have given node 6. Between 3, 4, I have given node 7. And between 4, 1, I have given node 8. If you want to add more nodes, you will start with node 1 and 5. In between the two, you can add node 9. Between 5 and 2, you can add node 10. And then you can go clockwise. So we will always choose either a clockwise pattern or anti-clockwise pattern such that node numbering is done appropriately and you get better results. One thing to note is in serendipity, there is no node at the center. Enhanced solution accuracy. The additional nodes and serendipity elements contribute to better approximations of the solution within the element. This can lead to increased accuracy, especially in regions with high gradients or complex deformations. Suppose if you have a zone where you will have complex deformation, if you add more number of nodes, you will get better solution which will be more accurate. So serendipity elements will help you in those situations. So you can see here, this is one element, you will add more nodes. Same way, this is a 2D linear element where you have only 4 nodes. This is quadratic, the first one. This is linear. And the third one is 3D quadratic because you can see the figure is 3D and you have added more nodes. So these kind of additional nodes always give you better solution. The third thing to discuss is reduced numerical diffusion. Serendipity elements often exhibit reduced numerical diffusion, which is the tendency for solutions to spread or diffuse numerically during the analysis. This is particularly beneficial in problems with sharp gradients or localized phenomena. So let's see this figure. If you see this end, it is a sharp re-entrant corner. Here, if you study the stress, it is possible that you may not get better results. But if you add more number of elements in this zone, you will get a better solution. If you don't have more number of nodes, what happens is the stress just looks diffused over the zone. You're not able to figure out which is the exact zone where you have more stress generated. So more the number of elements added over there, serendipity elements, you will get better results. So this is another application of serendipity elements in FEA. Next, we'll talk about improved convergence. We have already discussed what is convergence in FEA. You can just recall the concept before reading this. The enhanced accuracy of serendipity elements can contribute to improved convergence properties in iterative solution methods. This is valuable in large-scale simulations where rapid convergence can significantly reduce computational costs. Let's talk about this convergence. We have discussed about convergence of CFD element, or you can talk about convergence even of the stresses which is occurring on a beam, or the deflection at the end of the beam, or the number of degrees of freedom, as you can see here. So as you give more number of iterations for solving, you will get a particular solution. Now this needs to converge towards the exact solution. Say this deformation according to theory, which is the exact solution always, is say 0.02 mm. But when you are solving, you get a very high value. So as you increase more number of iterations for solving, that is, you solve the problems again and again iteratively, and you try to come to 0.02 mm as a solution. So if you are converging more towards this value, then you say that you are got a better result, and that is because of the improved convergence. Now this improved convergence definitely occurs when you increase the number of elements, that to the serendipity elements, such that you get better results. And if you read here, it's given that you will reduce the computational cost significantly, because if you do not use serendipity elements and you keep on running the solution for hours, what you're doing is just adding to your computational cost. So if you want to get better solutions and faster solutions, then you need to use more number of serendipity elements. Next advantage is better representation of curvature. Serendipity elements are designed to better capture curved geometries and variations in field variables. This makes them particularly useful in problems where accurate representation of curvature is essential, such as in structural analysis of complex components. So suppose if you have a curved geometry, then you will require more number of elements, such that, like the sharp corner I explained, if you have a curved geometry, if you create more number of elements, you get better solutions, and the accuracy of the problem basically increases. And if the component that you are using is already very complex, which means it is consisting of many parts, or the geometry itself looks very complicated, then in that case adding more number of nodes definitely gives you better solution. Next, potential for reduced element count. Due to their enhanced accuracy, serendipity elements may allow engineers to achieve similar accuracy with fewer elements compared to standard elements. This can result in computational efficiency and reduced memory requirements. Let's get back to this image. If you see here, this is the element. You have only one 2D element, but the number of nodes are 6, and you can increase, as I have told you. Same applies for this rectangle. This is just one element over here, and there are many nodes. So when you are solving with many number of elements, lakhs of elements, then your computation speed reduces, then your accuracy can be affected, computational cost increases. So if you have lesser number of elements, you have more nodes attached to it, what happens is you will get better solution. So that's the use of reducing element count, increasing number of nodes and getting better solution. Compatibility with quadrilateral and hexahedral elements. Serendipity elements are not limited to triangles or tetrahedra. They can also be formulated for quadrilateral and hexahedral elements. This versatility makes them applicable to a wide range of geometries and problems. So you have just seen a quadrilateral element when I showed you a rectangle. So here you can see hexahedral elements. These are the hexahedral elements where you have another node attached over here at the end. 1, 2, 3, 4. 4 nodes. And apart from that, you will be adding more nodes in between such that you can create a serendipity element. Like you can see here, there are 4 noded tetrahedral element. You will have 10 noded tetrahedral element. You can have 16 noded tetrahedral element, 8, 20, 32 noded, but the number of element remains limited. It does not increase. So what happens is you are saving on a lot of cost, increasing the speed and making the accuracy better. One thing to note, as I have told you previously, that there is no node at the center, and that is what serendipity element means. Next, simplicity in implementation. Despite the additional nodes, serendipity elements are often straightforward to implement in FEA codes. This ease of use makes them attractive for various applications. So now some key points to take from this session. While serendipity elements offer advantages, their use should be carefully considered based on the specific requirements of the analysis. The choice between standard and serendipity elements depends on factors such as the problem complexity, computational resources, and desired level of accuracy. So if your problem complexity is not too much, then you can go for standard elements. Similarly, if your computational resources are really good, or if you don't have a problem of reducing the cost, or you're not finding it difficult to deal with a lot of computation going on, then you can use standard elements. Similarly, if your accuracy is not a problem, then you can go for standard elements. But if these three reasons are present with your problem, then you need to go for serendipity elements. Engineers typically weigh these considerations to determine the most suitable element type for a given FEA simulation. So with time and experience, you come to know what kind of elements to use and how to go about with the elements such that you get better results. So with this, I end the session. I hope you have understood the concept of advantages of using serendipity elements in FEA. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.